So first of all, thank you so much, Dr. San Gupta, for having me over as the speaker for today's webinar. You're able to see the screen, okay?
Yes.
Okay, perfect. Okay, hello everyone, and thanks for joining this webinar today. So, I am Harish Krishnamurthy. I'm an associate professor in the Electrical and Computer Engineering Department, University of Houston, so I have been working on primarily power electronics, power conversion systems, and recently with the growing interest in the interaction between power converters and distributed resources, we have been looking at uh, energy storage and their application with respect to the integration and optimal usage and so forth. So today I thought this is a good topic, and again, with respect to the resiliency of electric grid from a modern weather perspective and also energy transition perspective, energy storage is becoming very critical. Again, another big change that is happening now is the AI data centers. So we'll cover a broad set of aspects. I'll probably skip some of the slides as we go, depending on the time that is available. But so here we go. Just a bit of agenda. We'll talk about the grid resiliency and some of the energy storage technologies, and briefly touch upon some of the health monitoring standpoint that we work on, and optimal energy management. So this is something I think everyone is very familiar with. Basically, we are moving towards a society where we have distributed energy resources like solar PV, wind turbines in bulk, as well as in close to residents. So there is power flow that is needed, not just from a central system, but also now moving along from a distributed system, and sometimes feeding to the grid as well. So the entire dynamics have changed so much, that has brought in several opportunities, but also so many different challenges. Like now, we don't have a very clear picture as it was before. How at any point, how much energy is being transferred through the transformers and so forth at the distribution side. So much of my talk today will be focusing on the distribution side, but again, we will connect that with some of the trends in the renewable energy sector as well. So so that two-way energy flow is a big advancement compared to what we are used to, from about 15 years ago. And in terms of some of the applications, so let me see if I can move this out. Okay. So with respect to some of the advancements, we are moving towards something called microgrids. Basically, microgrids are independently controlled electrical networks powered by local hybrid units. Like it can have solar panels, wind turbine, energy storage. So all these combinations together, and basically they may or may not be connected to the main grid. But some of the benefits here will be that if you have a microgrid, you might end up you might end up having a higher resiliency or lower resiliency depending on how you control. But just just as a keyword, please remember this, and then we'll come back to this term later on as well. Okay, renewable energy in numbers, right? So, of course, as we see, renewable energy is the fastest growing energy source. Last year, renewables made about 24% of the total energy, combined with hydropower, wind power, and solar PV. So that is moving very fast as well. Solar generation is rapidly moving. I have some numbers from Texas later on, and you will see how much solar energy is advancing in the US. And globally, renewables made up to 32% of electricity generation 2024. And if you include nuclear, that's 41% of the total energy consumption. So that is a major breakthrough, I mean, I would say, and it is only going to enhance over the next several decades, irrespective of several policies. But of course, the rate of growth will depend on the geopolitics and so forth. But renewable energy definitely, like, people have mastered it over the last 10, 15 years, and then the challenges have been pushed to different spaces. Like, so before going into some of those, let's look at what fuels some of these trends in the renewable energy sector, right? So the solar PV systems, looking at the residential PV, commercial, and utility scale, the general trend of the cost has come down significantly. So now what you're seeing is, like, the price of the solar panels per watt has actually gone down significantly. So this has made solar PV systems achieve cost parity, even compared to the traditional conventional energy sources in many locations. So I think recently there was a news from United Nations, which mentioned that solar PV, renewable energy systems have reached cost parity across the world, compared to the conventional energy sources. So on a broad scale, this is happening across the world, right? But with solar PV, like, some of the challenges that we see is, we have sunlight during the daytime, but if we have to use that energy during the night, we need some sort of energy storage capacity. So on the left, you're looking at a standalone PV system. So that standalone PV system is comprised of let's say solar panels, and then it's interconnected to the loads through power conversion here. And but you need some sort of a battery backup to power the loads when the sun is not out. On the other hand, you have a grid-connected PV system where the solar plants, like, through an inverter, are connected to the grid, even though you have the local loads. There is a grid connection. So during the evening times, or when the sunlight is not significant, you can take energy from the grid as well. So I mean, now we are seeing both sides of the solar PV system across different applications. This is an interesting graph. Like, I just put in to kind of explain how the solar PV systems work, right? So solar panels, they can be modeled like, in electrical terms, current sources. So what that means is, depending on the net irradiance that is falling on the solar panels, the higher they are, that actually leads to a higher current that can be generated. Like, basically, solar panels work with the principle of photoelectric effect that Albert Einstein received his Nobel Prize for that. So that photoelectric effect, the higher the solar insolation falling on a panel, the higher will be the current. So now if you see the trajectory, like, depending on how we take that energy from a solar panel, so the current fairly remains constant with respect to the voltage. So because it is a current source, we have to make that solar panel process a certain amount of power. As you can see, the bottom is the voltage to power graph at different insolation levels, like 200 watt per meter square and up to 1000 watt per meter square. So roughly on the Earth's surface, on the ground, that's kind of roughly the highest insolation that we can get. So in a meter square area, there'll be about 1000 watts coming in. And the problem is that, like, if you do not actively make the panels deliver the power that you see at the peak, it will just deliver based on whatever the load is, or some intermediate point. So there is something called the maximum power point tracking, which is needed, where again power converters play a huge role. Now, of course, you see 1000 watt per meter square, but the panels typically have about 15 to 20, maybe 22% efficiency. So if you have a panel that is 1 meter square area, even if 1000 watt of light energy falls on the panels, you get something like 200 watts out of the panels per meter square. Now on the right, which is something, again, there is a lot of misconception. Basically, we think that the hotter it is better for the panels. But if you notice carefully, the power graph actually shifts to the left as the temperatures increase. So what it means is that during the summer, even though the insolation may be higher, like, basically there will be more sunlight, the problem is that because once it gets very hot, the PV panels tend to not produce as much energy as they can. So we have to, some places we have to find ways of cooling them. So that is something, so all these, again, you can see the entire dynamics, like as the heat, the light and the heat change, the properties of the panel change a lot. So please keep that in mind. Now, a quick thing about wind energy systems as well. Again, wind power. There is, of course, when the turbines go around, the turbines create, the rotating motion, and this is a doubly fed induction generator, and this is a gear system. So if you have a gear system, so that gear converts a lower, the wind turbine rotates very slowly relatively, and that converts it into a fast rotating ratio, and that drives a generator. And please remember, this is a question that I have been asked several times. As simple as it seems so, but it's kind of, the voltage that is generated by the generator, it is AC, like not DC. So in this application, I mean, because it's a doubly fed induction generator, here the stator is directly connected to the grid, and at the grid frequency. But in many applications, if you're using like a permanent magnet generator, so which avoids gearboxes. So that will have these power converters directly on the lines. So you will need a rectifier that transforms the variable frequency AC to a DC, and from the DC, generally there is another converter, which is an inverter, that takes it to the grid frequency. So sometimes, like, you may be able to take this DC after the rectifier and take that to a collection point, and let's say if you're interfacing with multiple wind turbines at the same time. So this is something to remember. And there's always, like, the control with respect to the power converters, but you can also control the power generated using the wind blade pitches. So because again, when there is a variation, like, as the wind speed increases, the power produced from the wind turbine varies as a cubic function of the velocity. So, but after a certain point, like, the power will be maximized because the system is not rated for anything more. And at that point, you have to cap that power. So one of the ways you can do is by adjusting the pitch angle of the wind turbine. So you can see, like, the flat region here, beyond a certain point, you try to give a constant power. And if the wind speed goes beyond that during a thunderstorm or a hurricane, then we have to somehow lock the wind blades into a certain position. Otherwise, like, it might damage the wind turbine. So these are, few aspects of wind turbine systems. Now, what are some of the challenges? This is a very important term which is used in the energy industry, that is the capacity factor. So capacity factor is the ratio of the actual electrical energy output over a given time to the maximum possible energy output over that period. So what that means is, now you have, let's say, a solar panel, like solar farm rated for, 1 megawatt, but then over a period of time, let's say you expect, based on just the rating, you expect it to deliver, let's say, 100 megawatt hours over so many days in terms of the capacity, but it doesn't happen. There are multiple reasons. One is, of course, solar panels. The sun doesn't shine during the night, so that energy is not produced during the evening time. On top of it, like, there will be shading on the panels, right? Like, there will be cloud cover. All that reduces the net energy that can be taken out from solar panels. So in effect, if you see, the capacity factor of solar panels is only about 25%. And that also includes some aspects of curtailment, like, because sometimes there is excess energy already available in the system, and then the utility actually regulates the solar panels. They ask the solar farm to reduce the energy output, because otherwise, like, the demand supply, the supply will exceed the demand and potentially cause congestion in the grid. So in terms of the capacity factor, wind turbines are a little better because they have, mechanical inertia as well, and then the patterns of the wind changes a little bit less frequently than sunlight, so you have a better capacity factor for the wind. And if you see, like, nuclear, because they are operated nuclear resources, they are operated at the base load almost all the time, so they have a very high capacity factor. And now, micronuclear reactors are slowly becoming more and more prevalent. Like, instead of designing a 1 gigawatt or a 2 gigawatt nuclear power plant, people are trying to look at a few megawatts of micronuclear reactors, which can help. They are reasonably clean, right? I mean, of course, you need a lot of water, but they are reasonably clean. So there are ways. So how do we improve the capacity factor? So that is a very, very critical challenge that we are seeing in the utility industry. So there's another term um, which is becoming very famous nowadays, is the duck curve. Um, so there is, as you see, like during the daytime, the yellow trace shows how, the solar panel, power is produced for a certain system. This is in California. And the blue trace is basically the total load. So that's the total load. The red trace is actually the net load. So what is net load? So the net load means whatever is the total load, you subtract the amount that is produced through the renewable energy resources. So then you get the amount of load that needs to be supplied by the conventional resources, right? Let's say natural gas generators, or coal, or other forms of thermal energy systems. Now, what you can see is during the peak of the day, like when the sun is shining brightly, like, your net load, which needs to be provided by the rest of the resources, that goes down. But during the evening time, two things happen. One is that the sunlight goes down, right? Like, you basically, around 6 p.m., depending on the time of the year, the sunlight goes down significantly, and your net demand, as people start going back to their homes, turn on their air conditioning, the net demand actually goes higher. I mean, the total load goes higher. So what happens is, because of the combination of these factors, during the evening time, you can see that the conventional resources need to ramp up at a very fast rate. So almost 12, this is just in California. So this 12 gigawatt within 3 hours. So that is very fast. So a lot of times that, in order to avoid, if there is a mismatch in the supply and demand, you will have outages or other issues, right? So typically, like, people start doing the spinning reserve, and try, I mean, so many different things. And that's the reason why you will see that then the electricity prices go up significantly during the evening times. Again, I have a graph that shows the Texas grid. So this shape of this net load, right, with in terms of so it kind of resembles the shape of a duck. So that's why it is called a duck curve. Now, what is happening is in places where there is a high penetration of solar panels, the solar PV curve is increasing in magnitude, and then this red trace is going down and down, and at some point you will see that it just flattens out at zero. So the net load during the middle of the day is tending to be zero in many places, and that has now a new term that's called a canyon curve. So it looks like a canyon, no longer a duck, and that's even worse because now you have to ramp up in the evening, and the net load has to catch up much faster than what it is right now. So the increasing penetration of renewables without taking care of this duck curve issue or a canyon curve issue, that is something that can cause a lot of issues in the future. Now, the next part is, basically like the same duck curve, how it changes over the seasons. And on the right, you can see, like, that's the penetration of PV, right? So the higher the PV penetration in the grid, you're going to have more and more dip in that duck curve. So again, so that is something that has to be kept in mind. So how can we solve that? So what if we have a means to average that energy production and demand? So how, like, just some resources that can act as a buffer to handle this sudden variation in the net demand, right? So that's where it is becoming more and more important as we go into the renewable energy penetration. So it is becoming more important to go with energy storage systems. So energy storage systems can help, shift the time of energy use. So basically, at some point, like when there is more energy, you can help storing that energy on the energy storage resources, and then during the evening time when there is less energy available on the grid, we can actually send out the energy from the energy storage. So that energy storage is becoming very important. There are so many benefits. It also helps regulating the grid frequency, and it reduces the use of the spinning reserve, which are more like backup resources in case the supply and demand do not meet each other. So of course there are so many advantages that comes with energy storage systems. So let's see some of the different energy storage technologies. And if we have to interface energy storage technologies with the grid, we definitely need power conversion systems, because let's say batteries being the most common energy storage system type right now, battery systems are DC based, and then the grid is still predominantly AC. So we need power electronics to interface the energy storage systems to the grid as well. So now, what type of energy storage resources might be used in each application? So this kind of gives a holistic charge. So on the x-axis, you see the system power ratings, and like how large these systems can be built. And on the y-axis, you have the speed of discharge, right? Like how quickly can these energy storage resources be utilized. So on the top, on the right side of the spectrum, you have pumped hydro. So basically, the pumped hydro, they can be up to you can. So basically, the same hydropower mechanism that we use. What if we are able to pump the water from a lower side and pump that water up to a higher potential resource? Then we can use that pumped water later when we need to use to produce energy. So if there is excess energy, you can pump the water up the pumped hydro system, and then when we need that energy, we can actually use the potential energy to convert to make electricity. So but then it cannot be ramped up very fast, and there are other disadvantages to it. But like this is compressed air. You have the superconducting magnetic energy storage, different types of batteries, right? Lithium ion. So now we are starting to see, the battery energy storage system moving over closer to the gigawatt structure. So of course, this kind of gives a overview. Now, just a quick, heads up on the pumped hydro. So pumped hydro, as I mentioned, like basically you have two levels, like water at a higher level as well as a lower level. When you have excess energy, you can pump the water to a higher level, and vice versa. But some of the challenges, like it's very high cost, and you have several geographic limitations. We probably won't be able to use that everywhere. So that is something that restricts the use of pumped hydro. Then there is this flywheel. So flywheel structure, usually, it's basically storing the energy in really high speed, wheels, flywheels. So you can think of, the structure, you have a center knob. So as you have more energy, you kind of increase the speed of this rotary equipment, and then like that kind of keeps rotating for some time. And when you need to take back energy from the system, you can run a generator to take that energy back, and that time the speed reduces a little bit. So that is slowly becoming popular. Like several applications are using it. I think Amber Kinetics is one of the companies that is trying to develop flywheels. Of course, there are some challenges. These are mechanical systems, so if you are not very careful, uh, you can have explosion, and it can become pretty much dangerous if you are not very careful about that. There's another angle to hydrogen as a grid energy storage. So let's say instead of using batteries or other resources, what if we can produce hydrogen and store the hydrogen as an energy source, and then use a fuel cell or other means to translate hydrogen to electricity or heat. So that is called the hydrogen energy storage, which is slowly becoming popular. Some of the challenges include net lower system efficiency, because electrolyzer and fuel cells are together they may only have about 35 to 40% efficiency, round trip efficiency. And the cost of if we are not getting that energy purely from renewables, we might still end up having issues with greenhouse gas and so forth. So but this is something that is promising. So in the future we might see more hydrogen based energy storage. Now, coming to batteries, which is still the most popular, I would say. There are so many. I think the installed capacity in just the state of Texas, the grid scale batteries is getting somewhere around 13 gigawatts, and pretty much they are lithium ion based. So these most of these chemistries are lithium ion based. So just a few numbers. In terms of the energy density, we are going around 200 250 watt hour per kilogram. And we are trying to achieve 1000 watt hour per kilogram. That's a very difficult. It's turning out to be difficult, but we are trying to do research in that field. Like there are several faculty members even in our department who are trying to do that. And then the another thing is the cost. So right now it's hovering around 150 200 dollars per kilowatt hour, just the battery systems. Again, so there may be some variations within, but that seems to be roughly, around the value that we are looking at. So another part of it, we have to be very careful about is the cycle life. So the more number of cycles these battery systems go along, they will have degradation. So typically in the grid, we assume maybe anywhere from 3 to 5% degradation of the batteries every year when they are cycling in a normal fashion. Okay, so that's up to the main energy storage technology. So we also want to talk briefly about the power conversion systems. Now on the left, this graph shows the traditional approach of how the grid was before, right? So there used to be wind turbines, there used to be solar panels, but pretty much some inverters here and there. Predominantly, the grid was with the conventional rotating generators based systems. But now it's not just future; it's already here. But we are seeing more and more inverters on the grid. The inverters are predominantly made with power electronics, so that's why again power electronics is becoming very important going forward. So the problem with power converters is compared to a rotating machine which has inertia of the machine itself, the power electronics, they are just semiconductors which react very fast. So that inherent inertia in the grid is missing. So what that means is, maintaining the grid frequency and controllability and stability is slowly becoming a challenge as we go more towards a power converter based future. So, but then there are a lot of flexibilities that power converters can give. So some of the challenges that we need to move from is a traditional grid following control, where the inverters had to just follow what the grid actually produces. Now there have to be some inverters which need to now set the voltage at the microgrids or at the distribution level. So these, there will be some inverters that will have to work in some called a voltage control mode and set the voltage, while some of the other inverters will follow, right? So that's a big difference in the way that the future grid is going to work. Now, another part of it, any of these interfaces, the three-phase transformer is a major system. Like without the transformers, again, it becomes challenging to interface many of these resources. So the traditional way is to use a line frequency, silicon steel-based transformers that you see around. The challenge with those right now is that you know they just follow how the energy flows. Like they don't actively participate in the energy management. That said, modern day, I talked to some utility companies recently, and they were saying that it has become more and more difficult to get the inventory of the transformers itself, right? So it is taking a very long time to manufacture large transformers in the current market. I think because again with the global geopolitics and the availability of materials, so that huge size of the transformer, the material needed, it's becoming very very it's a bottleneck right now. So because of that, there are things like solid state transformers. Like basically, you work with higher frequency transformers and use electronics on either sides to convert from a low frequency AC to a high frequency AC and high frequency AC to low frequency AC. This way, the transformer material and size can be significantly reduced. So as we go higher in frequency of the transformer, we can significantly reduce the entire size of the transformer. But of course, you need electronics to process the frequency that can be interfaced to the grid, because otherwise the grid cannot handle high frequency directly. So that is called solid state transformers. It is so surprising that I at least talked to several investors and several companies with regard to solid state transformers, which have been very popular for like several decades, but they haven't been implemented onto the grids yet. But now there are more companies coming forward to implement solid state transformers onto the grid just for the flexibility that they can provide with power electronics. Now, some of this research that we had done before, like so how to interface battery energy storage systems to the grid using solid-state transformers. So this is a solid-state transformers. You can see some of the power converters on both sides that can process DC on one side and AC on the other. I don't want to go too much in detail, but basically, such solid-state transformers can be interfaced from AC to AC or AC to DC or DC to AC. Several combinations are possible depending on how you operate. So this is again interfacing wind turbine and battery energy storage systems with the grid. Again, I don't want to go too much in detail. This is solar panels again, interface to the grid and so forth. So this is something which we did recently using solid state transformers as energy routers. Looking at an offshore system where we can interface grid on one side, wind turbines or solar panels, battery energy storage systems. So we have been looking at how to efficiently manage different distributed resources using energy routers, which are primarily solid state transformers. So these cover several aspects of the grid, but there are some challenges with respect to the safety and reliability. So again, with this talk is partially about the resiliency as well. So on one part of handling the grid resiliency with the variable wind speeds and variable solar insolation, we discussed that energy storage systems can help with that resiliency. But some of the energy storage systems, like they may have some challenges with their safety as well. Like you may have seen explosion and fire in the news, like looking at some of the large energy storage systems. So the one at the top left is a flywheel system, as we mentioned, right? If the speed exceeds a lot, then some of those mechanical systems can fail, and which can cause explosion. And some of the battery chemistries themselves can cause explosion if the voltage in the cells exceed beyond a limit. So we do have battery management systems in most of these applications, but there may be different levels of safety which are needed to handle such cases. So of course there are, we are looking at, some researchers are looking at safety inherently from the cells. So going with solid state batteries so that you can eliminate the electrolyte and improve the safety. And then you have the cell level safety, safety devices, battery management systems, and so forth. And then there is a effective response. So this part is like, let's say if there is a fire, how do we respond to it? So our work predominantly goes in the green region. So we look at how to safely negotiate the charging discharging patterns of the batteries, and make sure that the batteries don't exceed their voltage levels. So one such research that we did is this multi-level power conversion system, where if there are we distribute the batteries in multiple modules and use power converters like something like this. So what this does is, if there are mismatches across the voltages in different batteries, we have a smart control system that can help balance the state of charge, and effectively all the four battery modules come back to the same state of charge and within a safe region. So using power electronics, we will be able to manage the voltages of different batteries. Now, there is one more angle that we work in our lab. That's actually an approach towards resiliency and health from a prediction perspective. So prognostic health management (PHM) is a very popular term used in the industry. So we try to understand how we can implement a PHM at power conversion and power distribution system level. So we do a lot of tests and characterization in our lab to understand the properties of power electronics, battery storage, and other systems, and try to understand how their life varies over the number of years that they are operating. So we do such things, and then we have again, just an overview of it. We have certain statistical models to estimate the remaining useful lifetime of some of these power systems, and we use machine learning to implement it at the edge. In the sense, we can implement all these smartness at the power distribution systems itself. Again, these can be 1 or 2 hour talks by themselves, but I just wanted to bring it to you that we are trying to assess the overall resiliency and then the remaining useful lifetime of the power distribution systems using smart algorithms and techniques which are data driven. Like, we don't want to just assume simulation data, but we are looking at it from a data driven perspective. So of course there are other work that we do in terms of digital twins. So the final part of this talk is on so let's say now you have energy storage, and we are operating the energy storage in a safe way, but we want to maximize the profit for the operator. So let's say you own if you own an energy storage system, or if you're operating the energy storage system, how can you maximize the profit, right? So that is what we have been looking at over the last 2 years. So just to give you a quick overview of the ERCOT electricity dashboard. So this is basically today's dashboard. Like, if you take up, if you go to this link, you will be able to see this. So one thing you see now is that the total capacity of solar PV in ERCOT, like is almost 31 gigawatts. So Texas is now number one in utility scale solar in the US. And Texas has been number one in terms of the wind, but this number, 39 gigawatts, hasn't been increasing, I think, in the last 2 years because of different policies and choice. And you have energy storage, which is, installed capacity close to about 14 gigawatts. Now, so that is one thing to remember. Then the second one is the system-wide prices. So this dotted trace is the predicted price for today in ERCOT. So it's kind of, this is the bus average, right? So if you notice how the trend goes, so the price of electricity is high during the evenings. Again, that's because we noted earlier that during the evening times, the supply and demand gap is reducing, which you can see on the right. So there is a wider gap during this time, as we are right now, and during the evening time, that supply demand gap reduces, and that increases the system wide prices. And you can see the prices going towards $80 per megawatt hour. So this is like right today. If you go to this link, you will be able to see that. So now, what if we take this opportunity of this varying prices? So what if we let's say, use our energy storage, so charge the energy storage during the low price times and discharge during the high price times, we can actually make additional profit using the energy storage, right? So that is what we have been looking at. So how can they help? So this helps in, of course, managing electricity. So the prices are higher in the evening, so we can make use of that. But not only that, right? So we can help reduce, like, if the demand is high during the evenings, and if we do not have energy resources, we saw that we need to add more energy resources during the evening time. So to avoid that, so by using energy storage systems carefully, we will be able to reduce the investments that's needed to balance the electricity grid demand, right? So that really helps, and it can improve the resiliency of the systems. It helps with demand side management, especially now when you have AI data centers. Such optimization techniques are becoming more and more critical, because there will be energy storage demand needed for data centers as well. So this is a overall system that we did a study with a hybrid energy storage system, like battery on one side and hydrogen based energy storage on the other side. We have this journal paper on IEEE. So basically what we did was we combined the benefits of battery energy storage system and hydrogen in a unique way using mixed integer linear programming, and try to understand how we can potentially use the energy storage carefully and maximize the profit. So our algorithm was able to handle these scenarios in such a way that, so what we did is, remember, like the number of cycles affecting the life of the battery storage. So we made sure that we do not let the energy storage systems to cycle fully more than 2 or 3 times a day. So we restrict that to the cycling of energy storage systems for 2 to 3 times. And we try to understand, like once we add that energy storage system, how much benefit can it provide to the operators. So this is a summary of let's say a community scale load. So community scale load, maybe 100 kilowatts or so. So now when we had a hydrogen storage, we to recover the cost of it, we can get almost like 17 to 18% rate of return. And if you add hydrogen and battery storage to the system, the way that we manage the resources, we can get a net 16 something percent annual rate of return. So what that means is, even if you consider the delivery charges, we should be able to get a return on investment, like complete return on investment within 7 years or so. So what this means is, let's say you are you operate a certain center, like a commercial center or a even larger center. So what if you bring in energy storage systems as backup for resiliency, let's say to protect against outage and so forth. And if you are able to use our technique to actually deliver some energy to the grid during the evenings, you can optimize in such a way that you can actually recover the cost of your investment in 7 to 8 years. This is after taking care of your own loads. So we did model some element of some loads that are needed, because let's say a supermarket or a downtown building and so forth. So you'll have your own loads. So even with that, we are able to get a return on investment for our battery investment or a hydrogen energy storage investment. This again, we can extend this to renewable natural gas or any of those resources. So that can provide you a sufficient return on investment within 7 years or so. So we did different types of loads. So this is like a commercial load up to 1 megawatt. Even here, return on investment is like again within 6 to 7 years. So which means that some of these advanced techniques can actually make it profitable for you in the long run with the system, because the systems themselves can operate for 15 to 20 years. Maybe you may have to change the batteries a little bit, but the solar panels and then the converters, they should operate for 15 to 20 years very easily. So the final couple of charts, I mean, again, this is a very busy slide, but what it actually shows is that, over the day, depending on the price of electricity, how the battery charges and discharges. So basically, like basically this is the hybrid storage with hydrogen and the batteries. So if you see, like this is a 72-hour window. There are sometimes when the battery is charged and discharged, you can see this orange is the discharge, and then the green is the charge. So you can see, like how many times the battery systems can charge and discharge. And those, when you see their discharge time, those are typically in the evening times. Like this is 19-20 hours. So 19 hours is 7 p.m. So this is during the evening time. So we used real world ERCOT price variations and then the load variations for the same. So now, as a summary, now we saw different, I mainly wanted to introduce different aspects of, the grid resiliency and energy storage systems and how we can make profit out of it. With more renewable energies, we have a lot of challenges, but that actually gives us opportunities also to make money. If you're an energy storage operator, and I mean, again, it doesn't have to be just the battery, but let's say renewable natural gas or other conventional types of energy resources, we have ways to optimize their operation and help recover the cost faster. So of course we have to additionally focus on power converters because we are going to need more and more power electronics experts in the world as the number of applications increase. So with that, I want to kind of summarize, like, we do need energy storage for a sustainable grid, which is also resilient. And again, I appreciate your time and for patiently listening to the talk. I want to thank our sponsors, the National Science Foundation, national academies, and other sponsors who sponsored some of this work. And I also want to introduce, that we are organizing this IEEE Intellect conference focusing on critical power and energy storage in Houston this October. So in case if you're interested, please visit the website, and that kind of concludes my talk. Thank you so much.